All right, today we are going way, way down into the subatomic world to meet a family of particles that are just fundamental to everything. They're called the leptons. We're going to figure out who they are, the rules they live by, and why they're such a massive deal in modern physics. So let's start with something familiar. You've definitely heard of the electron, right? It's the particle buzzing around the atom, the very foundation of chemistry and, well, everything you can touch. But here's the kicker. The electron isn't flying solo. It's actually part of a much bigger and honestly, a much stranger family.
And we're not talking about some distant, unimportant relatives here. The lepton family is made up of truly fundamental building blocks. You can't break them down any further. They're it. So if you want to understand the fabric of reality itself, from the phone in your hand to the most distant star, you've got to understand this family.
Okay, so let's do the proper introductions. What exactly is a lepton? What does it take to get an invitation to this very exclusive subatomic family reunion?
So here's the official description. A lepton is an elementary particle. That's key. It's not made of smaller stuff. It's got this quantum thing called spin of a half, which you can just think of as its own little internal angular momentum. But the most important family rule is this. Leptons do not feel the strong nuclear force. That's the super powerful force that glues protons and neutrons together inside an atom's nucleus. Leptons, they're total outsiders to that whole scene.
Now, like any big family, there are different generations. And we're going to start with the first, the one you're probably most familiar with. These two particles are the bedrock, the stable foundation of pretty much all the matter we see and interact with every day.
And the difference between these two is just fantastic. You've got the electron with its negative charge. It's a social butterfly. It forms atoms, it carries electricity, it interacts with light. Then you have its partner, the electron neutrino. It's got no charge, and it is incredibly antisocial. I mean, billions of them are zipping through your body right this second, and you don't feel a single thing. They just don't like to interact with anything.
You know, the neutrino is so hard to find, it was originally proposed as a ghost particle. Seriously. Back in 1930, the physicist Wolfgang Pauli noticed that in certain radioactive decays, a little bit of energy and momentum just seemed to vanish. Now, instead of thinking the laws of physics were broken, he had this wild idea. What if an invisible, neutral particle was sneaking away with the missing energy? It was a total long shot, and it turned out to be absolutely right.
All right, now things start to get really weird. If the electron is the stable, dependable sibling, the next two generations are its heavier, more exotic, and extremely unstable cousins. And it is amazing to look at how long it took humanity to piece this family tree together. The electron was found way, way back in 1897. Its heavier cousin, the muon, popped up in 1936. The even heavier tau wasn't discovered until 1975. And its partner, the tau neutrino, it was so ridiculously hard to find that it wasn't directly observed until the year 2000. That's over 100 years after the first member of the family was identified. So the family finally got its last name in 1948. The physicist Leon Rosenfeld suggested the name lepton, which comes from the Greek word leptos, meaning small, thin, or delicate. And at the time, it made perfect sense. The only ones they really knew were the electron and the muon, and compared to protons and neutrons, they were tiny. But, and this is where the story gets really fun, that name, chosen specifically to mean small, would eventually become just a little bit ironic, thanks to the family's biggest member. Say hello to the tau lepton. When it was finally found in the 70s, its mass just blew scientists away. At over 1777 of these mass units, the tau is, well, it's not small at all. In fact, it's almost twice as heavy as a proton. It's more than 3,400 times heavier than its little cousin, the electron. So yeah, we have a family named small ones that contains a particle heavier than the things that make up the nucleus of an atom. You gotta love that physics has a sense of humor.
So we have this wild bunch of particles. Some are light, some are incredibly heavy, some are charged, some are ghosts. What on earth makes them a family? Well, it turns out they all have to follow a very strict set of universal rules.
So yeah, let's ask that question directly. We've met the electrons, the muons, the taus, and all their ghostly neutrino partners. What's the common thread here? What's the shared DNA that ties all of them together into one coherent family?
And when you lay them all out like this, the family portrait, you can really see this beautiful symmetry. There are 3 distinct generations, and each generation is a perfect pair. One particle with a negative charge and one particle with no charge at all, the neutrino. the electron and its neutrino, the muon and its neutrino, and the tau and its neutrino. They're like perfect copies of each other, just at different weight classes. And here they are, the unbreakable family rules. 1. They all have that spin of 1/2. 2. Like we said, none of them feel the strong nuclear force. And 3, and this one is genuinely one of the weirdest things in all of physics, only the left-handed versions of these particles care about the weak nuclear force. You can think of it like their spin making them either left or right-threaded screws. For reasons we still don't totally get, the weak force just decided it's only going to talk to the left-handed ones. It's a fundamental quirk of our universe.
So this all rolls up into a really beautiful, elegant principle called Lepton universality. What it means is that, other than their mass, the fundamental forces of nature treat them all exactly the same. The universe doesn't play favorites. An electron is just a lightweight muon, and a muon is just a lightweight tau.
So let's just step back for a second and think about what this all means. This isn't just a quirky collection of particles for a physics textbook. This family is a truly fundamental piece of our reality.
So why does this all matter? Well, for starters, without the electron, you get no atoms, no chemistry, no life, no us. Simple as that. And neutrinos, these ghost particles, are absolutely everywhere, giving us clues about the sun and exploding stars. And on the biggest scale, the entire lepton family is a core pillar of the standard model of particle physics, which is, hands down, our best description of how the universe works.
And that brings us right to the edge of what we know. For decades, lepton universality was rock solid. But in the last few years, incredibly precise experiments are hinting that maybe, just maybe, there are tiny cracks in that rule. The muon might be acting just a little bit differently than its siblings. Now, these are just whispers right now, tiny anomalies, but they could be the first clues to brand new particles or forces that go beyond our standard model. It seems the lepton family still has some secrets to tell us. So the big question is, what new physics are they trying to show us? That's what's driving so much excitement in physics today. Thanks for joining me for this deep dive.